In this lecture, we're going to see a whole new kind of product, one which takes a cohomology class and a homology class, somehow mashes them together and produces a new homology class in a different degree. I want to describe all of this, again, like with the cup product, I want all of this to happen inside a single simplicial complex. We'll call that complex K. And as usual, it has a chain complex, which is written with lower subscripts, and a cochain complex, which is written with upper subscripts. And remember that the co-boundary operators of the cochain complex are transposes of the boundary operators with an index shift. We've shamelessly exploited this fact in the previous two lectures. Okay, and we assume that this is ordered or oriented. Let's just say, assume that the vertices are ordered. So every K-simplex, sigma, is uniquely describable as an ordered set of vertices. So V0 smaller than V1, smaller than blah, 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 all the way up to Vk. This will have an I front face, which is sigma less than equal to I. So you just collect the first I vertices in, here, and an I back face, which is where you collect the vertices going up from Vi to Vk. So the I front face is always going to have dimension, well, I, and the back face is going to have dimension K minus I think. Okay, good. So that's the setup. The important thing to note for the moment is every K chain, let's call it gamma, is a sum over simplices. So let's see what this sum means. This is sum over all K simplices. And this is some element of the underlying field F. So every K chain is, all this is saying, is a linear combination of K-dimensional simplices over the field F. Now, here is our new strange product. So we're going to take the cap product of an I chain, sorry, not an I chain, an I cochain, C. So this is the function sending all the I chains of K to F, the field, and a K chain, which is some gamma, exactly like the kind expressed as a linear combination of simplices above, is the new K minus I chain given by, and here we go. So this is the definition of the product. So you take C, and it's written like this. That's the cap gamma. And before I say anything about the right-hand side, I should say that that symbol is not \cap, but in tech it's \frown. So it's already sort of ominous and foreboding, but don't worry, it's going to be all right. Okay, so this cap product is sum over sigma, and now this is strange. This is again over K simplices. So I promised a K minus I chain, but I'm summing over the K simplices, so something terrible is about to happen. So you keep the indices that you had before from the chain gamma, and now you split each simplex sigma that you would have had for gamma into a piece that Xi can act on, which is the front I face, and then you leave the rest of it the hell alone. So what this does is, even though you're summing over K simplices, now this entire bit, this is in F, and this is a K minus I simplex, the back face, and you're adding this up. So, anatomically, it no longer looks like a K chain because you've taken an I bit of the first I vertices of the simplex and allowed C to turn them into a number, which means you only have K minus I dimensions left. So that's the definition of the cap product. And by convention, this equals 0 when C requires more, a bigger dimensional thing than sigma has. So this equals 0 whenever I is bigger than K. So this is only non-trivial when the dimension of the cochain is less than or equal to the dimension of the chain. So I less than equal to K for the purposes of this definition. Okay, now that we've defined a chain, we're going to play exactly the same game we would have played with the cup product, which is to try and figure out what the boundary of this chain is. So here is the formula for the boundary. Given Xi and I cochain, so let's write it this way. Actually, that's just fine. And gamma a J chain, K chain. The boundary of their cap product is given by, again, this is going to be a Leibniz type formula with a weird minus sign stuck in there somewhere. So this is going to be the boundary in the K minus ith level of Xi cap gamma. This is -1 to the dimension of Xi, which in our case is I. And then there are two parts to it. So in the first part, you leave Xi alone, and you take the boundary of the chain gamma. And I guess it's good to check here that this thing continues to have dimension I, and this thing has dimension K minus 1. So when you cap the whole thing together, you end up with K minus I minus 1, which is exactly what a boundary of a K minus I chain should be. So far, at least on the level of dimensions, this piece looks just fine. So let's get rid of the silly dimensions here. Okay, and so that's just the first half. You have another piece, so you subtract from this what happens when you take the co-boundary of Xi, which has to be the ith co-boundary, and cap it with gamma left alone, no boundary taken. And now again, you're going to have a I plus 1 dimensional cochain here, dimension K chain here, and then when you cap it, it's K minus I minus 1. So again, the dimensions at least check out of this formula. And the proof of this is so similar to the one for the cup product case that I am not going to write it down here. In fact, it is going to be an exercise. But the idea is exactly the same as we had before. So the first thing to do is that you can replace gamma by a single simplex of dimension K. So that's going to save some time, and then extend things by linearity. So that's good. And the second thing that helps here is there are two pieces to the right side, so apply them separately to that simplex and then add them up, and one thing from the first term cancels with the other thing from the other term, and everything works out just fine. Okay, so that's the proposition. And so there are some very nice corollaries, which is if you took a cocycle and you capped it with a cycle, let's see what would happen here. So because you have a cocycle, this term over here would disappear because it has no co-boundary. If the other thing was a cycle, this term over here would disappear, which would mean that this entire boundary is going to be 0, which means that the stuff that you have in here is a cycle. So for instance, you get things like this. So this is easy. It takes a little bit more work to check that co-boundary cap cycle is boundary. And that the other thing. So boundary here and cocycle here. That this is also boundary. So these are a little bit harder. But again, not so bad. Baby algebraic manipulations. They're, at least this one is in the accompanying lecture notes, and this one's an exercise. And this one's sort of completely straightforward. So, okay, so these are easy things to check, and therefore we conclude that the cap product also, just like the cup product, induces well-defined bilinear maps of cohomology groups. I mean, there's some homology and some cohomology, so I'm just going to just write it like this. Both are involved. And of course, again, we're going to call the cohomology version and the homology version is just going to be written the same way as it was written for chains and cochains. So it's going to take an I-dimensional cochain. It's going to multiply it with a k-dimensional chain, and it's going to produce a k minus I dimensional chain. But the magic part of this is if you did all of this with cycles, then you'd get a cycle. So cycle cross cocycle will give you a cycle, and this is all well defined. So anytime I said cochain, I may as well have said cohomology generator. And anytime I said chain, I may as well have said homology generator. So this is the sort of upshot of knowing the boundary of the cap product and then going through those 3 little checks for what happens when you have a cocycle, cap, a co-boundary, and so on. So that's about it for the definition of the cap product. I want to say a little bit about what it actually does. So if you remember, we had a picture of a torus before, where we looked at pictures of the one-dimensional cochains and then tried to figure out what their cup product would be. So something very similar happens for a cap product. So let's take a one-dimensional cochain. It's going to look something like this, and it's going to go all the way across around the back. So that's this one. And now I want to compare its cap product with 2 chains. So let's call this blue cochain that I've just drawn C. And now let's consider 2 chains. Here's one such. So let's call this gamma. And there's another one which goes this way, which we'll call, I don't know, delta. Okay. So what's the setup here? The setup is you have a torus, so all this this stuff here is filled in, and you have 1 cochain of dimension 1 and 2 chains again of dimension 1. And I just want to tell you what the cap product is actually doing. So here's what it's doing. So the first thing you notice is there are things homologous to gamma which will touch Xi. I mean, you could always have done something like this and gone back. So there would be some non-trivial intersections between gamma and Xi. But you can homologically perturb gamma to the actual red loop that we've drawn there that completely misses Xi. So there's no intersection. And therefore, the cap product Xi with gamma this has to be a zero chain because it's 1 minus 1 dimensional, but this is actually the number 0. So nothing shows up. On the other hand, if you take C within its cohomology class, going all the way around the torus, and you take delta and you try to perturb delta within its cohomology class, it doesn't matter what you do. You cannot unentangle it from C. No matter where you slide it, no matter what sort of perturbation you take, whether you decide to go on a walk that way, it's still going to end up somehow crossing C, and therefore their cap product will not be 0. C not equal to, in fact, it's going to be supported on some vertex of an edge that the chain and the cochain have in common. So what I'm trying to say here is that whereas the cup product was actually a product in the sense of discussing, sort of describing the product-like nature of the torus by generating the two-dimensional cohomology class as a product of two one-dimensional cohomology classes. The cap product is different. It's not really telling us, it's not a product in that sense. It's what's called an intersection product. It's sort of counting with multiplicity somehow intersections between embedded chains and cochains. So it might be difficult to think about good algebraic properties of the cup product, such as functoriality. Now, I want to say a little bit about one of the exercises to this bit of the material. So it turns out that the cap product does have a sort of remarkable functoriality, even though not all the arrows are pointing in the same direction. Let me tell you what I mean by that. So if f from K to L is a simplicial map, then we get sort of strange diagram of vector spaces. So for every I less than equal to K, so these are just dimensions, we get, so think about the cap product in K. So I'll write cap in K and cap in L. So the cap product in K is doing the following. It's going to take an I cochain in K. It's going to take a K chain in K, and you cap them together, and it's going to produce K minus I chain in K. Okay, you have the same story in L. So I cochain, K chain, cap them together, get a K minus I chain. Now there are maps between the homology and the cohomology groups being induced by our simplicial map. So this one is H upper I of F. That one goes up because it's on cohomology, so it has to point the other way. Whereas these two are for homology, and therefore they point down. So this is HK of F, and this is HK minus I of F. And now it turns out that this diagram, it's not really fair to say that this diagram commutes because there's nothing really that could commute here. But this diagram sort of morally in our hearts commutes. So what I mean by that is you take the sources of all the arrows and put something there. So if you look at the blue arrow that's going up, the cohomology arrow, so take the source and put some Xi. So Xi is going to be an I cochain of L. And then take a source of this arrow, gamma. So gamma is going to be a K chain of K. So they're not living, Xi and gamma are not living in the same on the same planet. I mean, they don't have the same dimension. One is I, one is K. They're not the same type of object. One is a cochain, one is a chain. And what's worse is they're not even living in the same simplicial complex. One is in L, one is in K. But there's a beautiful relation between various, the cap product in K and the cap product in L, which is something like this. If you take the top row, you have a gamma in the second spot, but nothing in the first spot. But of course, you have something that you could send there, which is the image of Xi under the induced map on cohomology. So if you look at the top row, you can do this. So this is H upper I F Xi. So far, we've produced a cochain here by moving Xi along F. So that's an I-dimensional cochain. And now, of course, it's available for capping with gamma. So once you've capped it with gamma, you've produced a K minus I-dimensional homology class here. Okay, let's try the same thing at the bottom, where you have a Xi, but there's nothing available immediately in the homology, the kth homology of L. But of course, you could take gamma and push it down. So that's going to be HKF of gamma. So that is going to live here in the K minus I dimensional homology. So gamma was in the kth homology of K, Xi was in the ith cohomology of L, and you've managed to produce one thing that lives up top and another thing that lives at the bottom over here. And of course, there's a map relating the two. So you could apply that map, which is HK minus IF, to this homology class. And then now you have two objects living in the lower right corner. And the magic is that these are going to be equal. So I think I've just given away a secret to one of the exercises, but I think that's a reward for sitting through these videos. All right. In our next lecture, we're going to see some amazing consequences of the cap product, particularly for manifolds. This is called Poincare Duality, and it is an extremely exciting and deep subject. So I'll see you there.